All right, so we're gonna go ahead and get started. Um, so this afternoon, we're gonna quickly go through modeling interpersonal pathways in the common fate model. I don't think it'll take honestly all that long. And then we're gonna move over into latent variable interactions, which to me is the really cool stuff that you'll never learn in an SEM class. So that's where that's the plan for the afternoon, and we'll see what happens. So we've already talked about the general recommendation is factor loadings over 0.70 for your common vector. And I just noticed a typo, that arrow is supposed to be the other way. So you generally want 0.70, but that doesn't always happen. So if you have low loadings, that doesn't mean you should abandon the common fate model. It just means you should think about, okay, if I have low loadings, that means the amount of variance at the dyadic level isn't where we necessarily want it. It's not at that 50-50 mark or that 59-41 mark, but maybe it's 40%, right? Maybe it's 35%. Maybe it's enough to warrant, I need to partial it out. But then, so I do that, and then I think about, okay, so what do I do with all that leftover variance? Do I want to just let that individual variance just kind of sit there? Or do I want to do something with it? And for me, if I see variance, I want to model it. Like that's just, I think if you do any statistics, you see variation, you want to know why there's variation. All right. And so that's what we're going to talk about now. We're going to talk about the individual parameters within the common fate. So low loadings can tell you a bunch of different things within common fate. If they're super low, that tells you there's nothing at level 2. Maybe it's you need to do an APIM. Maybe you don't even need to do a dyadic analysis. Maybe you just throw some cluster corrected standard errors on there and just run those variables on their own. I gave you the example of myself and my brother, my physical health predicting my happiness. And there's no reason to say why my physical health should predict my brother's happiness, just on average. We live 1,000 miles apart, we're 10 years apart. It doesn't make any sense. So if you have no variation at level 2, like we wouldn't, if we had a bunch of samples of me and my brother, just throw some cluster corrected standard errors on it and quit whining about the nested data, the nested structure of your data, and just move on, right? Easy solution. So that's one possibility. The second possibility is you have some variation at the dyadic level, but maybe that's due to the partner effects. Maybe that's due to shared covariation among the residuals, and you move to the APIM. So if you have like 25%, maybe a lot of that 25% is can be repartitioned into variance that's accounted for by partner effects or residual covariances. Or perhaps the low loadings is indicative of a latent difference score needing to be modeled. So we didn't cover the latent congruence model, but essentially what you do in the latent congruence model is you model a common fate factor, the dyadic mean like we have already, and then you model a second latent variable where you have one loading fixed to 0.5 and the other loading fixed to negative 0.5, and that represents a difference score between dyad. And so maybe that's why you have low loadings. It's because there's not a whole lot of shared variation because there's a lot of disagreements in the construct you are focusing on. So like I'm thinking about the co-parenting data, satisfaction with the custody arrangement. There might be a lot of disagreement there. And so using the common fate model doesn't make a whole lot of sense there. There is interdependence, but either maybe that's an APIM or maybe that's a latent congruence model. So you can model the disagreement and how that plays out into child outcomes, the co-parenting relationship and things like that. So that's another option. The third option, or I guess the fourth option potentially, is utilize phantom variables. So these phantom variables are going to come in. Again, I'm going to talk a little bit more about them in depth. Again, I don't think an in-depth understanding of what phantom variables are is needed here. Just know what they can do. So this is where you don't need to know what's going on under the hood in relation to phantom variables. unless you start doing some really crazy growth modeling stuff, then you'll probably need to know a little more. But for right now, there's not a whole lot that is needed. And so here are the standardized factor loadings. So I'll talk about a couple of things here. So first, the co-parenting. These items, in some way, shape, and form, they use the term we or the relationship, right? So those are clearly latent common fate variables that can be modeled using a latent variable. And you see the unstandardized loadings are fixed to 1, and the standardized loadings are 0.81 and 0.85. So perfect, right? And then you have the family violence. These are not those types of items. These are partner referential items, or so potentially even self-referential items. I can't really remember what the exact wording on them is, but the extent to which abuse contributed to the divorce. All right, so the divorce is a common event, but it's still kind of at that kind of maybe potentially more at that partner level, at that individual level. So you see the factor loadings are a little bit lower. All right, so that tells me that, 0.69 times 0.67, you're probably going to get around 46, 47% of the variances shared. So a decent amount, but it also tells us there's a lot more that meets the eye. There's some more individual variability around this. There's differences in perception that I want to model. All right. So typically, when we think about residuals, what do we think about? Just generally. What information is contained in a residual on average? Error? What types of error do you see? Do you commonly see in residuals? So measurement error, common method bias or common method variance, testing conditions, things like that. So all different types of errors. But if we think about, and a lot of times we view those as nuisance parameters. We don't care about them. We're trying to minimize them. And we're kind of just like, get out of here, right? With our errors, or we're ignoring them. Because we're really focused on estimating all the parameters in our model. We care about errors to the extent to which they don't, the extent to which they bias our parameter estimates. And if they don't bias our parameter estimates, then we don't care about them. We just kind of report them and we talk about variance explained rather than variance unexplained, okay? And so we largely don't care about residuals. We don't give them a second thought, but maybe we should. Maybe we should think about the importance of residuals. Maybe they contain information that is actually valuable to us that can be modeled. And so when we think about error in the common fate model, we have common method variance, we have measurement error, we have testing conditions, and all these other things. What other types of error are in our residuals? So remember, residuals is everything that isn't explained at the dyadic level. Bingo. Individual perceptions within the common fate model are located within the residuals. So what can we do? We can pull that information out using phantom variables. All right. So these orange boxes highlight where our individual perceptions are, right? Things that are, and how we think about that is things that perceptions or information about what I believe that is not shared with my partner, my dyad member, right? It's unique to me. And so this is, again, just to be a brief introduction to phantom variables. Again, I don't think there's a very good conceptualization. I've never really seen it explicitly defined. They say, oh, by the way, here's a phantom variable. They've been around since the 1980s with Rimskov. He started implementing these phantom variables in order to overcome a lot of limitations that occurred within Lisrel, which was the first really SEM software, and it was created by Euroscope. I think back potentially even in the 60s, maybe 67, 68. I think that's when SEM first started coming online in a significant way. And so they were developed to overcome a lot of problems with model constraints. You had to, in order to get models to run, you had to throw in some pretty wicked model path constraints in order for your models to converge. Because again, think back, what was computer software like in the 1970s, 1980s? crappy compared to now, right? Floppy disks were still like a thing, right? And so this is a really novel and innovative way to address some of those model constraints and overcome them. And how you specify them is they have a factor loading of 1. So again, it's going to be, you have 1 phantom variable per item. So you constrain that factor loading to 1, which means, and you may have seen these if you have ever talked about single indicator latent factors within a latent variable framework. You'll see that talked about a little bit. They're constrained to 1, which means that the residual essentially is it causes 100% of the variance in your observed indicator, right? And then you fix the error variance of that residual to be 0, right? And so within the common fate framework, we are going to be using those phantom variables, all right? And again, we set the residual variance to be 0, and we set the factor loadings to be 1 so we can pin that little phantom variable down. Because all latent variables, as we talked about, they're unmeasured. So how do we know anything about them? Is we have to give them a mean and we have to give them a variance, all right? So within the common fate model, we don't care about the means, okay? Or at least in general and on average, we won't care about the means. So we're not really going to specify a mean structure within the phantom variables. But if you're doing, like I'm developing and working on the dyadic growth curve with structured residuals, I have to deal with the means because the growth model, the growth process requires means. Those latent means are actually important to me now, right? That indicates the slope and the intercept. So I have to deal with the mean structure within those phantom variables, but here we do not have to do that, all right? And so, yeah, so we pin these latent variables down by fixing the residual measurement error to be 0, all right? And so for exogenous predictors, that's what we do anyway. I've already talked about this a little bit. We assume the distributions are fixed and known of our independent variables. And then for dependent variables on phantom, you fix the measurement error of the residual variance to be 0. And so they get their own error term now. And so you're still capturing some of that error term, right? The error is still going to be in the model. It's just going to be predicting it and going into the phantom variable. And I'll show you a pictorial representation of that here in a little bit, right? So here's a way I think about latent variables is these are the kids when you were at college and no one drank underage and you went to a house party or perhaps you hosted a house party and then you had people show up and start drinking all your booze and they didn't bring anything themselves. That's what latent variables are. They eat up information brought to them by other people, all right? So that's one of the ways in which I think about latent variables. Because then we have to pin them down. That's them eating up information, all right? Or another way you can think about it is they're gold diggers, all right? These are latent variables are variables that look pretty, that are awesome, that are sexy, and that we want to use. And then people, when they think about us using latent variables, they give us all the applause. There's no measurement error. And yet there's stuff going on in the background that isn't exactly the best, right? We have to pay a really hefty price in order to do that. And that's with they're using up pieces of information such as our means and our variances. And so this is probably the greatest pun or the greatest coincidence ever, but when you're using a latent variable, people love it when they see your model, right? Double entendre. Thank you. Okay. So I think about phantom variables more specifically as regulating the flow of information, all right, within a latent variable system. So they can either stop information from being transmitted through path tracing rules, or they can allow information. All right. And so when we fix the residual variance to 0, we're actually allowing information. We're pushing information from that observed indicator back into the actual phantom variables so we can use to model things. But also it can stop the flow of other information. And so I kind of think of it as a red light or a green light. You can either allows information to flow, or it will, again, prevent information. So here is what an example 2-variable common fate model looks like with phantom variables. So we have the dyadic level right here, like as we usually do. And we have dyad member 1 up here. We have dyad member 2 down here. And so normally we have a residual here, but now this is a phantom variable. All right. And we have a phantom variable over here as well. And so we have our factor loadings as we normally would. Right here, I am showing the standardized factor loadings because they're not constrained to 1. And so what's happening is we're theoretically believing that this latent variable is causing, at the dyad level, is causing an individual's response on X1, and all the other stuff that's not attributed at the dyad level is now residuals, but is now located, in the phantom variable. All right, stop it. And then we can use that to predict the phantom variable of the other construct, and that's an intra-individual effect.
So in concept, is that sort of kind of suggesting that the phantom variable predicts what we traditionally kind of call errors. That's kind of
Exactly. I would say for right now, and for the purpose of the common fate model, that's a fine way of thinking about it. If you get into more advanced stuff when there's with other phantom variables, like when you get into mediation and means and stuff like that, it gets a little hairy, but yes, exactly. And so here we don't have any error terms, as I've already talked about, because the distributions are fixed and known, but on our phantom variable of our endogenous variable, now we have our error term, and that's still correlated with one another. All right. And we still correlate these phantom variables together. And you'll notice we no longer have covariances between X and Y, between X2 and Y2 within the partners, because that covariance that we used to specify is now a regression coefficient, right? If you add a covariance in there, your model's going to not run, okay? Because you're now saying there's a covariance, there's an unexplained cause, but there's also an explained cause, which is that direct effect, right? So that is highly problematic for your model. But this is essentially what phantom variables look like. Any questions thus far? All right. So thinking back to the previous model is you have gamma 1, which is your dyad level effect. And then you have gamma 2 and you have gamma 3, which are your individual level effects. So it's so you have, let's say, family violence predicting a lower quality co-parenting relationship. And then in the residual portion, or the phantom portion, I'll call it, my unique perceptions of family violence contributing to divorce is associated with a lower quality co-parenting relationship that is unique to me, right? And so those phantom variables are, again, it's all unique information. So when you're talking about this, you have to specify this is at the individual level. Otherwise, you're going to confuse the hell out of your readers, right? All right. So I use this model in our JMFT paper that we're still awaiting feedback on. And essentially, the research question is, do reasons for divorce predict the quality of the co-parenting relationship? And is that indirectly related to emotional behavioral problems? And then we're going to only model that first portion right now. All right. So here's our model data fit. So our model fits really quite well. Again, you're only going to have 1 degree of freedom. Your CFI, your TLI are all good. And you have your residuals. Again, if you have something in the residual matrix that's highly significant, that is big ticket problems, because with a model with only 1 degree of freedom, you should be doing a really good job at rescaling your variances, your covariances, and your means. Right? So here are the effects at just the baseline common fate model with individual parameters. You have the effect of dyadic of raising children differently as a reason for divorce on co-parenting. All right, so there's -473. So for a 1 standard deviation increase in co-parenting being a reason that the couple divorced, there is a -0.473 unit increase in the co-parenting relationship quality. And then, because those factor loadings weren't high enough, we parceled it out into individual effects within mom, within dad, right? So this is female co-parenting individual or is unique to female raise unique is the unique, okay? So mom's individual perceptions of co-parenting being a reason for divorce was associated with a -0.094 unit decrease in co-parenting relationship quality that was unique to mom, right? And the same thing with dads. All right. So dad also had unique effects. So dads who reported that raising children was a reason for divorce, that is, again, that perception is unique to them. They also reported a lower quality co-parenting relationship that is unique to them and not shared with their partner. All right. So here's what it looks like. And these are I added in, these are I believe these are the standardized loadings. These were, I believe, unstandardized. Yep. All right. So here is that model that we saw earlier today with the common fate mediational model. The arrows are now in the correct direction. Here's our model fit for that one. So we have a decent overall model fit. You know, chi-square is significant, but we have, what is this, 1,600 people in here? Of course it's going to be significant. Or 1,800 people. CFI, TLI, both above 0.95, which again tells us that we're probably in decent shape. RMSCA is pretty good. I really look at the confidence interval around the RMSCA, and it's really quite small, really quite tight. So that gives me a lot of confidence that our model's doing really quite well. I looked at the residual matrix, and there's a couple of places where I kind of highlighted some potential problems. Where, you know, if you look at most of these, there's zeros and there's ones, maybe there's a 2 over here. But everything is really looking kind of good. There's a kind of a 3, but that's not really setting itself apart. But you look at, there's one right there and there's one right there that are 5 and 7, or almost 6 and 7. So that to me, there's some problems there. So for this one, the one that's 7, it's looking at joint custody and race is overestimated. I don't care as much about that because those are 2 covariates in my model. Race is dichotomous, joint custody is dichotomous. I just don't see that there. Of course, there's going to be some model misspecification when you're trying to, when you're covariating dichotomous indicators. So I might go and I might actually, this is where I would eliminate a covariance between those 2. But this one I need to be worried about. All right. This one, this male IPV, it's being overestimated with female co-parenting. All right. That relationship is too high. All right. And so here's our final model. And we're going to go into the residual matrix on the next slide. These are now, the error terms are now phantom variables. And now I am modeling with individual level effects. All right. So let's see. So here, this is the, when we think about the residual matrix, the way we get from father IPV to mother co-parenting, there's really only one path that'll get us there. So it's this path. So we go backwards and then we go forwards and then we go around a one-headed arrow and then we go forwards and there we are. So that tells me that it's probably this parameter is probably overestimated. This parameter might actually be too small. All right. It's probably not going to go up a whole lot. It might go up to 0.42, 0.43, 0.44. but that tells me via path tracing rules where my misspecification might be. And I might actually need to include an effect here from fathers to mothers. This might be one of those rare cases where there actually is a partner effect that is happening that I didn't model, right? Is all that making sense? Right. And so we actually have a couple of significant indirect effects, and those are shown in yellow. So we have family violence. The Zoom bar is going to be the bane of my existence. So we'll go over this one first. This is a phantom variable. So from mother E2 to mother E5, which is mom's individual perception of family violence, to mom's individual perception of co-parenting, to mom's individual perception of emotional problems, that is a significant indirect effect. There is a mediated effect at the individual level, in addition to the mediated effects that you see in blue at the dyadic level, all of which were significant. All right. And we have the exact same thing over here as I move my Zoom bar once more. So mom's residual on family violence is again associated with mom's residual on co-parenting, and it's also linked to mom's residual on conduct problems. Right? So we have yet another indirect. But we also have two significant direct effects, right? Mom's reports of family violence are still directly related to the conduct problem residual or phantom variable at 0.16. And you still have mom's effect from residual from family violence, E2 predicting E7 on emotional problems. So there's something else in this model that moms are dealing with, that moms perceive to be true, that we're not modeling here. So we only have partial mediation here, right? So we have indirect effects at the individual level for mom and at the dyadic level, but no indirect effects emerge for dad. All of these, there's a couple directional paths, direct effects that were significant, but none of them created a significant indirect effect for dads. All right. And so here's what it looks like in M+. All right. And you just, you throw these indirect effects at the within person level right below your model indirect effects at the between level. All right. So it's nothing overly fancy. And even though we have I would say a fairly substantially wide confidence interval, which again, perfectly normal, given the complexity of the model, we're significant at P equals less than 0.001. So we can say with 99% certainty that our effect is significantly different from zero, assuming that the null hypothesis is true. Right? And that's true for both. So from dyad rays to co-parenting to emotional problems, and IPV to co-parenting to emotional problems. All right. Same thing over here. So all of those indirect effects were significant, and here are the other two. I didn't go over the IPV ones, but they were significant as well. And here are the ones for dad. All right. And I'm sorry, I honestly, I got to figure out a way. I use F here to indicate father. Other times it indicates female. It drives me nuts, and I can't. It seems to be analysis by analysis on which one I use. But since it's co-parenting, I use mother and father. But if I use couple, it's male and female. Sorry, my apologies in advance for any confusion. These are the fathers. All right. And as you can see, the effects are really, really small. The confidence intervals are really tight, though, around dad. So we can actually say with a lot more certainty that there's actually no indirect effects of dad, because these confidence intervals, man, they are small, right? Those are dad. So I feel confident in skipping over this. So let's go into M+ and let's model these suckers. And I'm only going to have you model them for an independent variable and a dependent variable. I'm not going to have you do it within a mediation context. Let's just get you used to the implementing of phantom variables. So common fate mediation with individual parameters is your input file. Let's see. All right. Or maybe I am having you do it. I thought I. Does your made some changes at the last minute. Does yours have 2 or 3 variables? 3? Okay. Well, then that's what we'll do. I thought I changed it at the last minute, but apparently not. So, specify it's the exact same model we ran before lunch. All right. So we're going to specify our common fate variables here. And then we specify our indirect effects or our structural model right here. And I actually have it right this time. It was right to begin with. I don't have to make any changes. All right. And then I'm actually going to move this. All right, come on. There you go. We're actually going to move this up just for the order makes more sense that way. And then we're going to create these phantom variables. So you can really name it whatever you want. I did within relationship mindfulness, men. That's how I name my variables, right? And so again, your phantom variable goes on the left-hand side. That's on the left-hand side of your by statement. And then you fix that to 1. Right. And then once you're done creating the phantom variables, we're actually going to constrain the covariances of those with in-person effects to be 0. Right. So the with in-person relationship mindfulness is going to be constrained to be 0. For males, is going to be constrained to be 0 for within-person mindfulness for females. Right. And generally what I do is when I'm running these types of models, you run the most restrictive model, see if it converges, and then you can gradually start releasing parameters to be freely estimated later on. And so we're also going to fix the means to be 0. Again, I don't remember exactly, but I don't believe this is a necessary step, but we're going to go ahead and do it so you can get practice. So if you ever do phantom variables within a growth process, then you have at least some syntax available to you. All right. All right. All right, so we're here, so fix those means to be 0, and then you do the exact same thing to the variances or the measurement error of those observed variables, right? So just like we did earlier, fix those to be 0. So again, that's the phantom variable regulating the flow of information. Right? Then next, after all of those are fixed to 0, we're going to specify the means to be freely estimated. Oops. And then the final step is going to be modeling those with in-person associations. All right. So we have male male relationship quality being predicted by male dyadic coping. You have male relationship quality being predicted by male relationship mindfulness. And then down here, you have male dyadic coping being predicted by male relationship mindfulness. All right. So that actually, it's probably a little cleaner to put all the male effects up top. And then we can do tone portion. And you'll notice how there are no partner effects in this portion of the model. Right? Because I'm assuming all of that mutual influence is accounted for already at the in the latent variables that we've already specified. All right. That may not be true, but it's certainly possible. So I'm operating under the assumption that the individual level effects of each partner are not going to mutually influence one another. And then finally, we specify our indirect effects. Get rid of that one. Just that'll make the model run faster. I'm not sure if this one takes a little while or not. I'm going to go ahead and run it. All right. So for those of you still working, I'll give you another few moments to create your syntax. When I was actually running this and testing the model, I'm shocked it actually converged, given such a small sample of couples, but it worked. All right, so we'll begin to scroll down. We'll look at our summary of our analyses. All right, so everything looks good. All right, so everything looks good here. There's no outlying variables. Again, this data set has no missing values at all. And then we scroll down to our chi-square, and it is non-significant. Our RMSEA is really, really low. But again, look at that confidence interval. It's extremely tight. So I can say with a lot of confidence that we have, actually, it's not, it's extremely loose. I'm sorry. My apologies. I thought it was 0.151. Huge confidence interval. Again, so that tells us the RMSA is probably not it's really biased in small degree of freedom models, so we can ignore it. SRMR, we haven't talked a whole lot about that one. This is actually one of the fit statistics that I kind of like a little bit, but it behaves really, really well on a very consistent basis. So even in bad fitting models, this isn't a discriminating fit index. but I think to me, it actually provides a decent amount of information because it's essentially the average amount of misfit per, I think it per parameter in the model. So it gives me a good index of how biased or unbiased my model is overall, but I don't use it as a deterministic factor in the estimation of in the determination of whether or not my model fits. All right. So here this is at the dyadic level. So dyadic mindfulness did not have a significant direct effect on relationship quality. Not surprising because that's the IV and relationship qualities are DV. Instead, the effect was fully mediated through dyadic coping. All right. So we have full mediation here. And then dyadic coping was a significant predictor, not a significant predictor, but when we go down to the standardized, you will see that I believe it is. Yep, dyadic coping, it is. And I think did I use MLR? I believe I did. I used MLM. MLM is the same thing as MLR, but as long as you have no missing data. They provide slightly different corrections. You'll never use MLM practice because you always have missing data unless you're doing like multiple imputation. That's one case where you might use MLM, in which case I would just use MLR anyway. And so let's go to the within portion of the model. All right. So these are the within portion, this is within person association. So males' relationship mindfulness is a significant predictor of male relationship quality at the individual level. So the direct effect at the dyadic level is fully mediated. And so relationship mindfulness had no direct effect on relationship quality, but for males at the individual level, it still does. So how mindful males are when they communicate with their partner is still a robust predictor of how satisfied they are in their relationship. All right. And so let's look at that for females. It's not a significant predictor. Right? It's even negative, right? So that tells us something, at least clinically, presuming that, these results are perfectly valid. And given the small sample size, I can't really say that, but it tells us that the way men perceive communication and mindfully communicating is actually intimately tied to their relationship outside of how they cope with problems together. And that's not the case for women. Right? And then we also have dyadic coping and mindfulness is not significant for men at the individual level, all right? But it's not significant for women at the individual level either. But when we think about dyadic coping, we have for women, it's highly significant, right? So the more women individually perceive the higher level of dyadic coping, the more satisfied they are. But we have, what was this? Where's it? For males? Oh, that was for males. My apologies. We have for females, it was not significant, right? So we're seeing individual level effects on males, which is interesting. So when we tease apart what is relational and what is unique to males, we're actually seeing males value communication more so than we might actually think. That's more of an impact at the individual level and how satisfied they are, right? But when we think about our theories and how we think about communication, it's generally attributed more so to females, but our results here say something a little bit different, right? And so again, that's where parceling out and teasing out what occurs at the dyadic level and what occurs at the individual level can provide us a lot more nuance. All right. And then we can scroll down to standardized. All right. And then we can look at R squareds, and we will get R squareds at the individual level for each of our endogenous variables. All right. And again, I don't report the significance of the variances. I just report the amount of variance. Because again, This really, really complex model with a really small sample, our standard errors everywhere are going to be just astronomically large. All right. So any questions about modeling this at the individual and dyadic indirect effects? I know it's a lot, and I know it's a lot at the wrong time.
I think, just like other things, like, I think that I sort of following along, I need to do a few more tests for two, but this weekend, I think I'm following along basically with the concept.
Okay. In these will, and again, I'm using kind of contrived examples. So if you don't connect like to some of the substantive stuff, running it with your own variables, I think that's really the best thing that you can do. Absolutely. And just getting practice. That's how I learned this stuff. Is just practicing and learning from your mistakes, learning from when your models don't converge, and not throwing your computer out the window when that happens. Getting close, getting infinitely close, but not actually doing it. All right. Okay, so that is modeling individual and dyadic parameters with the APEM. So we can do more. We're not going to, because I do want to get to the LMS interaction, latent structural variable interactions. Whoops. We can constrain those actor effects, as we'll call them, to equality to see if there's a significant difference there, right? And if there's partner effects, we can include all those partner effects as well. And one thing that again, I'll say one thing. I'm a big advocate of doing this type of thing, even if it's not a theorized type of effect. I think that's how we advance theory is, if you have to have a defense for every single parameter in your model, then science by definition will stay static because it has to be completely developed by something that already exists. So we don't move anywhere. So again, I'm a big fan of constraining these pathways. All right. And it'll give you using the delta method of test, whether or not these are significantly different from one another. You can also use the model test command within M+ to get the same, you might get a different value, but it's using a walled test, all right? But whoops, didn't want to do that. Oops. All right, so that's the next step that we would potentially take is constraining those to be equal. But there's even more we can do, all right? Whoops. Stop. Man, this computer has a mind of its own. We can add in those partner effects, even though we believe they're not significant. It might actually attenuate the actor effects, right? And so our actor effects, they were significant, but when you add in the partner effects, they fall to non-significance, right? So maybe those with in-person effects aren't all that meaningful after all. Once we include the mutual influence in there, once we include the actor partner part of the model in there. So again, I think that's just a way to really get at the unique contributions of the within person effects is to use those partner effects, perhaps not in the way we would traditionally think about it, but in a way as a statistical control. So that's when I talked about what ways to use the APEM, I think yesterday and perhaps morning, and you're really interested in like one parent's outcome. And so you just include the other parent as kind of a control variable. And that's one way to use the actor partner interdependence model is to account for the variation of that partner effect. And we're doing that exact same thing here. Okay, we're going to do moderation in the common fate model. But we're going to start more generally and talk about moderation within structural equation modeling. So traditionally, I've already gone over this when I talk about APEM moderation, so I'm not going to do a whole lot. You create it by either constraining parameters to be equal, or you create a product variable, right? Your IB times your moderator, right? That's the traditional way of testing moderation. But the common fate model uses latent variables. Latent variables are unseen. So how do we test that has become the questions, and people have been kind of arguing for about 20 or 30 years. What is the best way to do that? So I think this started in, say, the mid 80s when latent variables started to really come online, and then people realized, okay, I want to test moderation, but how do I do that? Some are going to be very elegant solutions. They're going to use more calculus involved. They use more advanced analytic techniques, and some are going to be a little bit more practical. And my guess is, if I asked you how would you do it, I'm guessing you would probably come up with one of the answers. And so one of them is rage Hulk. All right, and what rage Hulk is doing is you are multiplying each of the indicators on one factor with each of the indicators on the other factor, like you would in a traditional moderation approach, and all of those product terms become indicators on a single latent factor. All right, so it's just rage hulking and just doing all of those computations. But if you think about it, if you have a latent variable with 6 factors and a latent variable with 5 factors, that's a lot of indicators, right? P times P, that's where P times P plus 1 divided by 2, that's how many indicators are going to be on that latent factor.
And with the rule of thumb, I know it varies for like how many people you would want per participant, but I mean, if you would have also, I've heard like from 10 to 20 people per item is a good general rule. Would that follow if you wanted to try and do rage Hulk method? You'd have to have even more participants to account for that, do you think? That might be more esoteric.
I mean, I have an answer, but I take me down a rabbit hole. So I will do my best not to go down a rabbit hole. I don't think those general rules are worthwhile in any way, shape, and form. I don't follow them at all. So to me, what you're really getting at is how many people do I need to detect an effect, which is essentially a power question. Instead of using those general rules, this is where you run a Monte Carlo simulation study and you throw in how strong you think your effects are. And I think that will tell you how many people you have. Especially in moderation, we're probably going to be underpowered no matter what, honestly, because the effects are so freaking small. We're just going to be underpowered. So I don't abide by those types of, 5, 10, or 20 indicators or people per indicator rules. Because what I found is that you can actually increase power by adding more variables in small samples because you're reducing your residual variance, right? And so I think a lot of those guidelines are just thrown out there, and people take them and internalize them as that is, the tablet that Moses, is reading off of, right? And that's not the case. So it's a long-winded way of me saying I just don't even think about those general rules. I think about how big my effect sizes are. And so within the product indicator approach, within the common fate, it's not going to be all that unwieldy because you really only have 2 indicators. You might have 3 if you're doing like family level, like parent, child, kid. But even then, that's going to be 9, and that's not unheard of. That's completely fine. And so even in most common fates I've seen, it's just going to be 2. So 4 indicators loaded on a latent factor, not bad at all. So what you're going to do is, if you're going to take this rage Hulk approach, or this product method approach, is you're going to double mean center them, which means you are going to mean center them before you create the interaction terms, and then you're going to mean center the interaction terms, right? And essentially what that is doing is, even though in structural equation modeling within a moderation framework, we're only really concerned with the covariation, we're not really worried about the mean structure. When you have interaction terms, it actually affects your mean structure, and it can create convergence problems. And so by double mean centering them, what you do is you make those means in your structural equation modeling 0, which allows for convergence, right? So that's why you double mean center. And this is available in any SEM package. You can run this type of model. So you can run it in Levant or in Procalus or Stata or whatever it is. And so it's much more accessible than other methods of testing latent variable interactions. All right. So this is essentially what it looks like in Amos. All right. You have your IV, you have your moderator on the up here, so dogmatism and agreeableness, and then you have your interaction term, which is a product indicator approach of all of them, and then you throw some residual covariances on them, and then you can use that to predict your dependent variable. All right. And you'll notice here that it's there's covariances, just as in the usual way that you would have them in a multiple regression type model, or in just another typical way of testing moderation within structural equation modeling. So there's a YouTube video. So I just want to forewarn you that we talked about Rage Hulk, and then the opposite is like Sexy Hulk. And I found these images way too easily. I just Googled Sexy Hulk, and these were like the first 3 images, and I was far more concerned about finding these images. I expected to have to dig and dig and dig, or have AI create them for me. Nope, they're already there. And so this is a complete flip of the mindset. So before, we were creating a latent variable with all the interactions, which makes a lot of practical sense about how we test interactions, right? But now we're going to do something completely opposite in a lot of ways. As I mentioned before, that even when you multiply 2 completely normally distributed variables together, their product is not normally distributed, right? So we're always going to have, unless you have some really funky data to begin with, you're always going to have a lot of non-normality in your data. And so one way of thinking about non-normality is through latent class analysis, through mixture models. Because when we think about non-normality, in the way we think about latent profile analysis or latent class analysis, they make exceptionally strong distributional assumptions that your data are non-normal. That is a requirement for a latent class analysis, because it's trying to identify those subgroups, right? And so what we can do is we can conceptualize the non-normal distribution of the interaction term as a series of normal distributions, each of which is attached to a specific latent class. All right. So we're doing a latent class analysis, and we put all of those classes together, and it forms our non-normal distribution that's created by our interaction terms. All right. So this is what's called an indirect application. Most of you have probably heard about finite mixture modeling, latent class, latent profile analysis, latent transition analysis. And you've probably heard about it identifying subclasses of divorce or childhood abuse or marriage or whatever it is. That's a direct application. This is an indirect application because we're not trying to estimate the classes based on substantive variables or interests. We're trying to formulate these latent classes based on a series of normal distributions that we can put together, create a joint likelihood, and model the parameter estimates and our standard errors. All right. So again, completely elegant. It's using tons of calculus. It's a solution completely out of left field, right? Who would have thought of this other than these guys? Like this is unbelievably creative, right? And so this is kind of what it looks like. If you're not familiar with latent profile or latent class analyses, that's what your distribution should look like in some way. That's a very simplified version of it. But essentially, this is your class 1. This is your class 2. And when you put them together, it creates this joint distribution that you observe it within your data file. All right. The problem with LMS, you don't get any fit statistics. You get a log likelihood, and that is it. Well, you get AIC and BIC, no RMSCA, no CFI, no TLI, because you have to use the integration algorithm. That doesn't allow for fit statistics to be estimated. Same thing if you're doing a SEM with a dichotomous outcome. You also don't get fit statistics. right? So what it does kind of limit us, it doesn't allow us to test whether or not the model data fit is actually adequate, right? So one of the things that people have argued is if you have a good model data fit without the interaction term where you can estimate RMSEA, CFI, TLI, things like that, if you add in that interaction term, it's not going to hurt your model, is the assumption, right? Just adding in one more parameter, how would that kind of hurt the model data fit, especially if we're thinking about the terms that we're adding are just multiplicative terms of what's already there, okay? And so generally that's a concern. You can do a likelihood ratio test, which you all have probably learned are using the chi-square, but you can also do a likelihood ratio test using the log likelihood values, because that follows a chi-square distribution. So you can still test whether or not the model, the model with the interaction term is significantly better than the one without. You have to use those log likelihood tests values, all right? So here is your your null value right here. That's your log likelihood value right there. The negative 1.958.69, right? And so you take that and then you take the log likelihood value of your second model with the interaction term in there. Hopefully it goes down. You want a smaller log likelihood. You want that to be closer to 0. And then you evaluate whether you calculate the difference, and then you evaluate the number of parameters that you're adding to the model, which will be one additional parameter. And then you will see whether or not that's statistically different. And you do that by doing, essentially it's a chi-square difference test, because log likelihood values follow a chi-square distribution. And so if your log likelihood is greater than 3.84, then it significantly improves the model. Okay. When you are doing this, you cannot use robust maximum likelihood. You have to use regular maximum likelihood, and then you can tack on robust later once you've figured everything out in your model, right? But you don't use your adjusted log likelihood. But here's just an example, right? And so we have the model 0, and here's our -2 log likelihood, and we have model 1, and here's our log likelihood. So we have a difference test of 46. The P is significantly different, and so it's way higher. So our model fit significantly improves, right? We have a better model data fit now. That we have added the interaction term, because again, this value gets smaller, right? Because we want our log likelihood values to approach 0. And that's where maximum, remember I talked about maximum likelihood, trying to maximize the probability that our parameter estimates reflect the population. You can also think about it as kind of like the inverse. We're trying to minimize the likelihood that it doesn't. All right, and that's what the -2 log likelihood kind of represents. And there's calculus involved on why they're negative and all that. I'm not going to go into that. I have only a very rudimentary understanding of that. But essentially, it goes into the maximum likelihood formula. With LMS, you will get standardized and unstandardized effects or output, right? When you have the product indicator approach, your standardized effects are not correct. All right, you have to rescale them. And so I report unstandardized effects. I'm going to use the product indicator approach. I generally report unstandardized effects anyway, because it just makes more sense to me. I don't know how to make sense of interaction terms at the standard deviation unit level. All right. And so one way you can do that, if you would like to standardize, you can do that in M+ in the define command. You can standardize all of your variables before you even run any analyses. All right. In this case, you only interpret the unstandardized effects. You're going to standardize your variables beforehand. So this is what it looks like. And notice how what's different here than the product indicator approach. There is no covariance between the interaction term and the main effect in the moderator of the independent variable and of the moderator. M plus will yell at you. It will not estimate your model if you try to covary your interaction term with the other two. Right? It doesn't allow you to do that. Right? And so within M plus, how you're going to specify your interaction term is going to be special. You're not doing this in the define command. Right? So you're doing that actually in your model syntax, and you're going to name your variable right here, which is inter, and then you're going to use the vertical pipe, which means given, right? So interaction given IPv X width is going to be what creates that latent variable interaction, and then you have your second variable. And here I'm using two common fate variables, IPV or family violence, and co-parenting in the prediction of dyadic level of conduct problems, right? All right, so we can move over into M plus. All right. I had trouble getting this one to kind of converge, but I think I ended up getting it right. So it should work using the demo version. So again, hopefully it'll cooperate, but I got it to work once. So we are going to use the data file. It's called CFM OM LMS. And I originally ran this. The reason we're using couples 3 is because I ran this in the couples data set that we've been using, and it wouldn't converge because the sample size was way too small. So I had to increase the number of folks in our sample. So here is the interaction, or the code for the interactions. So we're using dyadic coping inventory, relationship mindfulness, and couples satisfaction index as our three common fate variables. And so in your analysis, you have to specify type equals random in order to calculate the latent variable interaction using LMS. And you have to do algorithm equals integration, right? And then estimator will be robust maximum likelihood. One of the downfalls of LMS is we don't know a whole lot about what are the implications of non-normality in our variables and how that affects our parameter estimate, since it's done using latent class analyses. There's still a whole lot of research to be done around that. So right now, this would be the gold standard, but there still remains a few problems. Not problems, things to consider. Be careful, warning signs. All right, so scrolling down to the model syntax. We have our three common fate variables. This should become second nature. Here is our creation of the interaction term. And the interaction term is a relationship mindfulness and dyadic coping. All right. And it doesn't matter which one goes first, right? Because multiplication, essentially. And then you'll specify your structural model. And we're gonna take another deep dive into using the plot command within M+, and so you'll want to label your parameters. And then you still want to retain your covariances between all of your male reported and all of your female reported residuals among the three common factors that we have, or the three latent factors that we have. And then now we are going to scroll down and do the model constraint, right? So because I standardized the variables up at the top, the values here are in standard deviation units, right? So it's 2 standard deviations, 1, 0, -1, and -2. Mhm. Again, you can create your own labels here. These are just the ones that I taught and that I've created myself. And then here is your simple slopes equations, right? So we have our main effect plus our interaction slope plus the level of our moderator, right? So you can see here that we're assuming parallelism. We're assuming that the effect of the interaction is the same across the entire spectrum of our x variable, right? And then down here we have our plot command, and this is so we can look at and visually see what the interaction looks like. Okay. And so we're going to plot our very high, average, low, and very low effects. And we're going to loop our moderating variable, which is dyadic coping. That's the way I have it set up. Technically, it doesn't matter. Your IV and your moderator, since it's multiplication, it's arbitrary in which one is which. And then we have 4 and -4 as our bounds on the graph. And then 1 unit is the unit, I never know how to describe this. There's probably a word for it. It's 0, 1, 2, 3, 4 on the graphs. Those are going to be our units. 1 unit between the tick marks on the graph. That's the best way I can describe it. And then down here we have our simple slopes equation, and then times the value of our moderator. All right, and then we can go ahead and we can run. Actually, take off this. Take off the outliers. It'll take about a minute or two to run with it in there, but it does take quite a bit longer to estimate the model. So I would recommend taking it out. So here's the syntax in case anyone still needs a little bit of time. All right, so in this one we have 305. We have 305 dyads, so we have 610 people in this analysis. And we'll scroll down. We'll look at our skewness, kurtosis, all of those things, make sure everything kind of looks good and no problems. So model estimation terminate normally, so we're good. And this is what your fit statistics look like. All right, so this is essentially all you get. Here is your -2 log likelihood. All right. And then you have your AIC and you have your BIC and your sample size adjusted BIC. And if you've done anything in mixture modeling, you'll use these criteria a little bit more than you would just in normal structural equation modeling. And so here we are going to look at our unstandardized output only. Okay, we'll briefly glance at the standardized to get a sense of the a variance explained, but that's really about it. Since we standardize our variables beforehand, that's what we're going to be looking at. And so here is our here are our primary findings is we have two significant main effects, and then we have a significant interaction, right? And then we have our covariances, and then we have our residual covariances across the reporter. And so now we can go down to the new and additional parameters portion of the model. And we can kind of get a sense of what is happening. All right. And so we can see when dyadic coping is high or very high, there's not a non-significant interaction. All right. But when it's medium, low, or very low, then our simple slopes they are now significant. All right. And so now let's go look at the plots. So let's look at the loop plots. So open in view, and this will be very low moderation. And so we already know this one's non-significant. It's close, but it's non-significant. So when dyadic coping, as it gets bigger and bigger and bigger, when there's low moderation, it's non-significant. Right. And then we go to when there's the -1. I think that -1. Our slope is still non-significant, right? Because these blue lines that represent the confidence intervals cross 0. And then we'll go here. And we have at med mod, and then we have at high mod, and then we have at very high mod. All right, so these are our simple slopes analyses. These are the plots. All right, so these are the things I would include probably every significant simple slopes plot along with the overall plot that I showed you at the first thing this morning with high, medium, and low all on the same graph. I would report both. All right. So, and you really need that singular plot with all the simple slopes on it to really get a solidified interpretation of what these actually mean. All right. All right. So how I do that is I go to the unstandardized effects, and I have an Excel spreadsheet that I use. I need to know the main effect. I need to know the interaction effect. I need to know the intercept of the dependent variable. And I think it's for male that the interaction is significant. So I use this, and then I just have my centered and uncentered mean predictors, and you can just write up a little code in Excel to get those plots for you. Or you could do it in R, easily done in R, I'm assuming. I don't know how to use ggplot 2, but I've heard it's pretty incredible, and I've seen it looks awesome. So that's how that would be my next step in plotting this. Any questions about LMS interaction? Again, in your document, you report all of these simple slopes. Right? And then they're in the never mind. Sorry, I was going to go down a different hole. So one thing that we haven't done yet that we will probably want to do is we're explaining crap ton of variance. And the 78%, that's a lot. I'm normally happy with 20, 15, and we're accounting for 78% of the variance. Why? Because we're using latent factors, and we're getting rid of the measurement error, right? So we might want to figure out how much variance is our interaction term actually accounting for. So we have 78.3. And so what I'm going to do real quick is I'm just going to block this out. And then I'm going to get rid of that interaction term. Get rid of that. We're going to run our model. We'll scroll down to standardized estimates. 617. So that interaction term is explaining 17.2% of the variance. So we don't have covariates in here. This is just a very naked model. That's still obscenely high. I've never seen anything that higher than that one paper I reviewed that I told you all about yesterday. But when we get rid of measurement error, this might actually be possible to actually get these meaningful effect sizes. So if we have, I don't know the power that we would have, but if we have 300 couples, 600 people, and a effect size of 0.17, I bet this is adequately powered. I bet we have power over 0.80 in order to, and that's generally the standardized recommendations for power. So 4 out of 5 times, if there is an effect, you will actually find it. So you have an 80% likelihood of not committing a type 2 error. That's what power is. All right. So I'm turning this into a paper, right? I was just dinking around. You obviously I was putting things together that I thought would go together, and it turns out it works out really, really well. So yeah, we're gonna see what this does in terms of actually getting published. So yeah, so let's take a break. All right, so in the final stretch, I know you all are probably feeling it. I know I'm feeling it. And so I'll be as brief as possible. So essentially, I told you all, I didn't think we were going to get to the random intercept cross-lagged active partner interdependence model. So what I did last night is I went and created it for the common fate model. And so we're not going to go over it. We're just not. But know that you can apply, you can look at within coupled deviations over time on a construct. So couple level support, intimacy, you can look at how that deviates over time. All right. And that's essentially what this is. All right. And I provided syntax for it all. And so if you want to model it, you certainly can. I got pretty far. I ran into some model convergence issues. All of these are freely estimated except for this CC, it's this path right here that's problematic. So that C will actually have to go away for it to converge, but essentially you can get within and between estimates of effects. And all the same things that we've already talked about in terms of the random intercept cross-like pattern model. So now I'm going to we're done with statistical models. Those are all the ones that I had scheduled us to talk about. Everything else was just kind of a bonus. And so there's a lot of other syntax related to distinguishable dyads and things of that nature. But here's kind of my recommendations on when to use the models. And again, these are general rules and not hard and fast blood oath rules, right? So when your research question is focused on mutual influence, that's when you go with the APEM. How I affect you and how you affect me. If that's at the center of what you are trying to understand, then I think that's probably the best way to go. especially when there's little variability at level 2, which is at the dyad level. If you're a multi-level modeler, it's that random intercept, all right? And when individual levels of variables are of primary interest, your APIM is probably gonna be your best option. We'll talk about in the Dyadic class, hybrid models, where I talked about my depression and my partner's depression impacting our communication. So you can also do it that way too. But you'll want to include the actor partner in there in some way, shape. For the common fate model, that's when your unit of analysis is at what's happening between partners or what is shared by partners or what commonly affects. That's when you utilize the common fate model. Even if your factor loadings are weak, again, I just showed you how you can model it individually, right? So you can estimate individual level effects which are actor effects in the APIM and dyadic level effects that are not in the APIM, right? So essentially, that's one way to think about it is you can have actor effects in both models, but it's just how you're conceptualizing the non-independence. Is it at the dyadic level or is it through partner effects? That's really that's one of the differentiating factors between the two models. And when you want to consider rates of change over time at a dyad level, you want to do the common fate. And that's the common fate growth modeling, and which we'll talk about more in the we're not going over it, but you have slides on it, and I'll do in the class, we will go over the common fate growth model. All right. And I walk you through how to specify it and model building and M+ code. And then one of the other things I'm developing is using phantom variables within the common fate to estimate a within person effect over time. So the final thing I'm going to go over is my recommendations on reporting and what you should be doing in your analyses. Keep in mind, I wrote these at 10:30 at night, the day before the workshop, because it's something I wanted to include, but I have been so focused on ensuring all the syntax files were right and editing 550 freaking slides. So this unfortunately fell by the wayside, but it'll give you some generalized recommendations. And also I'm going to turn this into a peer-reviewed article as well. So hopefully at some point you'll see this. Pre-registration. You've probably heard some people talk about pre-registration. I'm becoming a bigger fan of it, not necessarily to the extent to which people want it to happen. In terms of like registering your hypotheses and like open science framework, I think either reduce tenure requirements and allow us to do better research, or just live with the fact that people aren't going to pre-register. You don't really get to have your cake and eat it too. So I'm a big fan of pre-registering, so you don't dilute yourself or gaslight yourself into modifying your model in a way that's inconsistent with your theory, or you have confirmation bias where you have your model, there's misfit, you fix it using modification indices, like, haha, I knew it all along. We want to get away from that, right? So I think that's one of the things that pre-registration does. And so I think pre-register your hypotheses with your research group, with your advisor, with a colleague, with a peer. And that way that keeps you honest in terms of what you can do. Because I'm guilty of this. I had a P equals 0.05. Throw in an extra covariate, P equals 0.048. Hallelujah, I got a publication, right? And so you want to get away from that. It doesn't mean that those findings are legitimate. It just means they're potentially not legitimate, right? And so you just register your hypotheses and talk through things before you run your analysis. I'm also a big believer in the way I do it. I do not write my introduction section until I have my analysis kind of done for the most part. But I talk through it. Here's the theory I'm using. Here are some citations I know about. Such and such a study found this, this, and this. So pre-registering your hypotheses, even with yourself, writing it in a Word document, and then running your analyses and then seeing to what extent they're supported. And then if you make modifications, just tell the reader, just be honest about it. I don't expect you to be omnipotent and know every little thing, because when you are working with your data, It's kind of like going to war. You have a plan, but your enemy has a say in what you do, right? So if you read anything about D-Day, we were supposed to go in on June 5th, but there was a storm that happened. And if you've read anything about D-Day, we know it was an absolute cluster. Nothing went right. The Americans, we almost screwed it all up. The British did fine, and everyone in Canada did fine. It was us. We screwed it all up. So our enemy has a say in things. And so the same thing happens in our modeling. When we're modeling, we have a residual covariance that we need to include that we didn't expect. Just be honest about it. That's all I'm asking. So pre-register your hypotheses and just be honest. People have recommended pre-registering your syntax. I think that is the stupidest thing I've ever heard in my life. If you're saying pre-register your syntax, you've clearly never ran an SEM in your life, ever. So I think that's dumb. So people say pre-register your syntax. Then I would ask them, do you know what sampling variability is? And the answer is going to be no, right? Theory. You have to have a theory, especially in the social sciences, where we are subject to perception, we are subject to bias. We can't hold things in our hands. So you have to have a theoretical framework that supports your analytic decisions, right? And so your theory should necessitate dyadic analyses. So if you're using like life course theory, but you're using a dyadic analysis, I'm not seeing the connection there. What about life course theory? Then you say, oh, the convoy model of social relationships. Okay, there we go. I can now understand why you would need a dyadic analysis. But life course theory on its own, it's kind of like this catch-all umbrella theory that everything's life course. If you're a developmentalist, of course you're going to be a life course theorist. So you need to add some more specificity into that, right? A big thing that we didn't talk a whole lot about, but I did vent about for a second, is if you're doing longitudinal analyses, you need to convince me that the amount of time between your waves is acceptable. Because you could absolutely have change, but you miss it. So I was reading a study about like a yoga intervention for post-traumatic stress. They did pre-test and they did post-test. There were no significant decreases in any mental health problem. Then they did a 9-month follow-up. That's where the effects were found. All right. And so an analogy is when you go take a shower in the morning and you turn the hot water knob, does it immediately come out hot? No, it doesn't. And so if you're only measuring it based on you turn the knob and you put your hand on, is it hot or not? You're going to miss the significant effect. So think about at what rate do your variables change? So again, I wish I had time to do this. I'm going to try to carve out time. I want to do a systematic review looking at marital quality and depressive symptoms. And I want to stratify it using only longitudinal studies. I want to stratify it across time. Where are the strongest effects? Is it at 6 months? Is it at a year? Is it at 2 years? Is it at 3 years? I think systematic reviews and meta-analyses doing things like that could be just like, I mean, that's gets cited 2,000 times type of paper, because then you're literally quantifying the lag in which you are, it provides a theoretical framework for the lag that you should implement. Levels of measurement. I've already beaten that to death. I'm going to beat it to death just a little bit more. Discuss levels of measurement in your literature review and in your measure section. Because you could have a theory that says, I need a common fate model, but if your measures don't support it, no, you don't. Right? Or you need to get new measures. All right. And this should come in before you collect any data. You should think about your level of measurement. Right? It's okay to have individual level measures. It's okay to have partner level measures. It's okay to have dyadic level measures. Just be intentional about it. All right. Because there are some things that could be dyadic, but I only really want individually. I don't care about it at the dyadic level. So that's perfectly okay. Just know what you want. You need to have a very explicit rationale for your analytic procedures. And so what I mean by that is, it's not we use an actor partner interdependence model to examine blah, 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 blah. It's an actor partner interdependence model effectively answers questions related to mutual influence, while other models, such as the common fate model, they model what is shared between partners, which is not the focus of our theoretical background. Therefore, an actor partner interdependence model is the best choice to answer the proposed research questions. So you are literally beating the reviewer to the punch about why didn't you use this model? Why didn't you use that model? Right? So not the concerns out in your manuscript that a reviewer is going to potentially see. Because nothing pisses me off more than seeing something, me writing a comment, and then them addressing that comment. Pisses me off when I'm a reviewer, right? Piss me off. Right? Establish distinguishability, whether this be in the ISAT model with the APIM or the doing it within the common fate model by constraining those covariances and those intercepts. Establish that. Because if you don't have indistinguishability, one, you have more power, and two, you can include your LGBTQ couples. You can include your opposite sex couples. You can include opposite sex twins couples. Then your findings actually have greater generalizability. Your studies can make more of an impact. It's going to be cited more often. And you should report it. And I honestly don't care if it's in the online supplementary material. I really don't. As long as you say we had indistinguishable dyads, results are in online supplementary material, good enough for me. All right. What framework are you going to use? Are you going to use MLM or are you going to use SEM? Because there are differences. We focus mostly on SEM here. But if you're doing intensive longitudinal data, intensive longitudinal dyadic data, SEM taps out. After like 4 or 5 time points, especially if you're modeling growth or change over a really small period of time, SEM's done, can't handle it. So you're using multi-level modeling. But if your question is more about lagged effects, why are you using multi-level modeling when it can't estimate those effects? All right, so just provide a rationale for why SEM over multi-level model, right? Or why multi-level modeling over SEM, right? Report bivariate correlations, means, standard deviations, and variances. And I'm not good about this, so I'm being a little bit of a hypocrite here. Report them from your covariates too. Because what you can do is if you report your entire, the variances, covariances, and means for your entire model, if you give that matrix to me with the means and standard deviations, I can actually run that through SAS or through R and reproduce your entire model. I don't need anything else other than that variance covariance matrix and that mean vector. Okay? If I use MLR, if I'm using MLR, that becomes a problem. And if there's missing data, that becomes a problem too. But do that so you can enhance reproducibility, so people can actually reproduce your results. A picture's worth 1,000 words. For the love of God, even if you're doing a baseline APIM, do a picture. Do your moderation, run a graph, all right? Don't present your results in tables. I can't stand tables when I'm trying to read things. I like, just visualize it for me. Don't make me do more work. So I mean, when possible, I try to have a blank theoretical model, and then I have a second figure that with parameter estimates, right? Report omnibus and local fit indices. So report both. I promise you all, no one in our department has probably reported local fit indices in a single paper, except me, because I do it now. But it gives you more information, and it overcomes the problem with fit indices within SEM, and then run sensitivity analyses and identify influential observations. Right. I had one slide on it. We didn't really talk about it a whole lot, but with the moderated mediation paper, we actually found 3 influential cases. And when I removed when I ran the full model, it didn't work. So we had a non-positive definite matrix. I removed them. Perfect. Pristine, right? And then you have to provide a rationale for why you remove them. That's it. That's all I got. I have more material. but I don't think I have it in me to present it, and I don't think you all have it in you to absorb it in a way that might actually be helpful. So that's the 2-day workshop on dyadic data analyses. And again, we'll do way more depth in the fall, but we're also going to expand it to include growth modeling and longitudinal analysis, which I did not cover here, other than the random intercept cross-site panel model a little bit. That's it.